Hello, dear viewers. I'm back, as said, with the topic of gallium chemistry and labeling, a deep dive. In this presentation, questions like these will be answered. It is why chemistry, what are the physical characteristics, physico-chemical properties of gallium, which are the trending gallium radiopharmaceuticals, when and how is the best labeling possible, and what are the challenges of the labeling, and how do we consider that this gallium radiopharmaceutical has been passed. So the basics of gallium chemistry and labeling will be understanding or trying to deeply dive into and pick the pearls of these answers. So why chemistry of gallium? Firstly, chemistry is the study of matter, its composition, properties, structure, and how it interacts with energy in the medium. Now here, because we can prepare the PET radiopharmaceuticals in-house, the gallium-68, as you know, it is a short-lived radioisotope, and we can see a potential workhorse PET radionuclide in this gallium-68 because we become free from the need of cyclotron, and we can depend on the cost-effective generator, its parent being germanium-68, whose half-life is as long as 271 days, and so a secular equilibrium is followed, and we can get this gallium-68 of just a short life or half-life of 68 minutes. And so this becomes very important to know the chemistry of gallium. Firstly, we will try to understand the physico-chemical characteristics of gallium. Its symbol is Ga, and atomic number being 31 and atomic weight being 69.723. It stands here as a part of periodic table. You can see here it is in the group of boron. Okay, now let us see what's the next point. It is about the solid and liquid transformation at just room temperature 20 degrees Celsius. It is solid, and 29.6 degrees Celsius becomes liquid. So it melts at room temperature. Solid to liquid transformation, or you can see the physical changeover is so frequent or so easy for gallium. It is between this 10 degrees. Let us see the next point about electronic configuration, how the electrons move in which orbitals of this gallium as an element, as an atom. The 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. So it is argon plus argon's electronic configuration plus 3d10, 4s2, and 4p1. So that makes it a reactive metal. While argon, as we know, it is a stable element. Now, group 3A element, as I told you, it's a boron group, and it has important metals like gallium, indium, thallium, all three of which have a radioisotopic form, which has been used in nuclear medicine. It has 31 known isotopes, ranging a mass number from 56 to 86, and the most used radioisotopes are gallium-67 and gallium-68. Now, the gallium-68 is the one in much of talk, and it is a positron emitter, as we have already talked about it. Now, the gallium-69 and gallium-71 are the stable isotopes. The trivalent coordination chemistry is what this gallium follows, and this is what it talks about, the reactivity of gallium with organic compounds, and we'll see about this as the presentation grows. Now it has a +3 oxidation state. Primarily, it is a strong, hard Lewis acid. Slowly, we'll come to know what is this Lewis acid. Now this is an ion analog, and so it follows this kind of mechanism of movement inside the body once it is injected, and it binds to the transfer in the plasma protein, and it reaches the region of interest accordingly. So it acts like an analog to iron, the gallium. So firstly, before we go into the Lewis acid and all the coordination chemistry, let us understand about the special decay pattern. In general, we think about generator produced as single photon emitters, and the positron emitters are produced by the cyclotron, isn't it? But here, in the case of gallium, it is the gallium-68, which is a generator-produced radionuclide, as I already told you about the germanium-gallium generator, as you can see here also, and it has an 89% positron emission and 11% electron capture, while actual cyclotron produces the gamma source, and that is gallium-67, because generally it is a switchover that is thought about, that cyclotron will produce only positron emitters, but it is not so. Here you can see the variant of this typical pattern of gallium of the cyclotron produced positron emitters and the single photon produced only by generators. No, this is going to change in the case of gallium family. It is different. So this is what I want to just highlight before we go to the next point. And you have to also know about the gallium-67 being a much longer lived radionuclide, can be used as a replacement for gallium-68 in radiopharmaceutical designing and development, because as an element it will not be having any difference, and this kind of extrapolation is still possible. And you can handle a longer lived and research for the research purposes, this gallium-67 becomes helpful. Now, important terms, the Lewis acid, as I was telling you, it is about the electron pair acceptor. What is Lewis acid? This is our gallium, which it is a strong, hard Lewis acid, which will accept the electrons. As an analogy, I've shown here the two friends, Lewis base and Lewis acid. You can call them by name like this, and that means, let me go back to this slide. Okay, here the electron donor means it has both the electrons which are going to be shared by this Lewis acid, and Lewis base will be from the Lewis base itself, because it has this lone electron pairs. But does it donate or give it away just like an ionic bond? Will it give it away these extra electrons? It is not so. Even it needs, the Lewis base also needs these electrons. So it is like these friends are playing cricket, and Lewis base has a ball also and a bat also. But is he going to just give it away to the Lewis acid? No. He's going to play with this Lewis acid. This cricket will be a kind of a bonding that they are going to have, and but both the materials, or both these electrons, or you can say in this game it is a ball and bat, will be given by the Lewis base. This is what it means. Okay, and so the shared electrons are from the Lewis base, but these shared electrons will move around the nucleus of the Lewis base at nucleus also, and also around the Lewis acid. That is, you can call it as an acceptor, but it is not completely going to accept. It has to share it with the Lewis base. Now, this makes them have a dative bond or a coordinate bond between them, and so then it is kind of a game that starts between them, and they are in a relation, and they have this game that they are playing, that cricket bat and ball can be considered as electrons, which they have to move around with both. Okay, so this is what is the coordination chemistry. Study of compounds that have a central atom. Often it is a metal and surrounded by the molecules or anions known as ligands that form the dative or coordinate bonds with the central metal, as you can see here. Now, what is the story? The story is this metal will have not only one friend who has cricket bat and ball, but he can share with the other two friends also who have cricket bat and ball. Okay, and he will not have any bat and ball, but he will play the game. This is what our gallium does, and this kind of trivalent chemistry, coordination chemistry, is possible for gallium. This is what it means. Now, often 67 gallium, as I have told you, it will be used as a replacement for gallium 68 in a radiopharmaceutical development. Because this designing for that a longer lived radionuclide is important. Now, let us go for the coordinate complexes of gallium. What do they form complexes with? They form organic with the organic compounds to form organometallic complexes. As you can see here, we know that gallium is a Lewis acid which does not have the cricket bat and ball, that is those lone pair of electrons, but all the others like this amine, as you can see in the next point, it is the functional groups having strong Lewis bases like electron donors like oxygen, nitrogen atoms, as you can see here in this small example, and that will be carboxylic group, phosphonate group, thiol, phenolate, hydroxynate, and amine groups to form strong coordinate complexes. Okay, then this is also going to be thermodynamically and kinetically stable at physiological conditions. And why you need this kind of, why this is important, this kind of chemistry to be read and studied and even explored, because we are going to inject this gallium radiopharmaceutical inside the body and we want it to be stable. This bond or this relation should not get broken once inside the body. Then the purpose of injecting this radiopharmaceutical inside the body is totally lost. So that is why it's very important that they are supposed to be thermodynamically and kinetically stable at physiological conditions. And these gallium chemistry of radiopharmaceuticals have to be studied. So now gallium-3 as a trivalence, that is why the 3 oxidation state, as we have seen, is suitable for complexation with polydentate ligands, both cyclic and open chain structures. Cyclic means this aromatic compounds, as we know, and open chain means aliphatic compounds. So these organic compounds, they will complex with the gallium metal, and that is they are the polydentate ligands. And that is what is meant by organometallic complexing. And if the ligand, besides binding the metal cation, also presents a functionality of an amine or carboxyl group that allows the covalent bonding or coupling to a targeting vector, it is called as a bifunctional chelating agent or bifunctional chelator. Then that can be example as a very common example is diethyl triamine pentacetic acid DTPA, our common actually used for 90 technetium renal agent, glomerular functioning agent, that DTPA only here also, but it has it works as a bifunctional chelating agent to form stable complexes together. What does it mean? If there's a mediator, this you can call it as a mediator who will keep this radioactive gallium attached to the vector or to the actual ligand. So this is just going to hold both the hands and making it more stable complex, because the gallium directly to the vector may have some kind of steric hindrances, or that may not be very strong as organometallic complex. Then this DTPA adds on to the strength of the gallium vector bonding. That is why the BCA or bifunctional chelating agent can be used, which has these kind of groups, amine groups, carboxyl groups, and all that, which will complex and form the complexes and hold the radioactive substance as well as the vector together. Okay, so this is how you can call it as a mediator, which will hold the bond of gallium and vector. Now let us understand the importance of this gallium with respect to its solubility as a chemistry of the study and the solubility, whether how much it dissolves in the solvent. So gallium readily dissolves in hydrochloric acid and potassium hydroxide with the evolution of hydrogen. Actually, that is why the hydrochloric acid is used as the eluent or that solvent which will bring out the gallium 68 from the germanium gallium generator. And this is one of the reasons why we study the gallium chemistry. Here we are seeing the solubility aspect. It forms insoluble gallium oxides in water, but it is soluble in ammonia and potassium hydroxide. So that can be the agent, or that can be environmental conditions which are required to be present in the medium so that the gallium compound is soluble. Now, at pH range of 3 to 7, it can hydrolyze to insoluble trihydroxide if its concentration exceeds nanomolar level. So a very small concentration is required, and at this pH 3 to 7, it can become, if at all its concentration increases, it can become an insoluble trihydroxide. This is what it means. So 3 to 7 is almost like acidic conditions. Now, this precipitation, however, can be avoided in the presence of some stabilizing agents, and there's a buffer which is to be used also to maintain a particular pH so that the reaction can be run properly. And now here, the physiological pH at that the solubility of gallium is high due to gallium hydroxide, 4 minus ions. Okay, and this is mostly in this form, gallium hydroxide. Okay, and now here the conditions of labeling. Let us see what are the optimum conditions. The pH has to be, we have to know what are the different parameters. We have to maintain a particular pH for the labeling of the radiopharmaceutical to really occur. And the temperature has to be maintained, which has to be whether you need a boiling or whether you need any kind of and if boiling temperature, boiling water bath is required, all this has to be optimized and during the design of the radiopharmaceutical gallium preparation. And then the absence of metallic impurities in the yield, especially the parental impurity, becomes an issue. Germanium 68 parental radionuclide with such a long half-life should not get into the reaction while also and or inside the patient's body, because that becomes a radiation safety issue because it will be constantly emitting the positron emitter. And these metallic impurities can also cause the hindrance of a reaction or bonding of this gallium to the desired, to get a desired radiopharmaceutical, gallium radiopharmaceutical. So even the daughter, that is zinc, which is itself a granddaughter for the matter, germanium 68, gallium 68, and zinc. Then zinc is itself a metal also, and its presence in a larger amount also can cause the hindrance or the interference with gallium 68 label. The time of reaction, how long you have to keep for the reaction, keep this optimum conditions so that the reaction occurs in the best possible way. And you cannot keep it as long and long, 1 hour or so, because gallium 68 itself is a very short-lived radionuclide, and all this becomes very important to be standardized during the radio pharmacy development, radiopharmaceutical development. And so the chemistry has to be known. The freshness of the yield. And this freshness of the yield, again, the point of zinc buildup also stands important here. So the yield has to be really immediately just prepared, freshly prepared, so that you don't have the metallic impurity, as this point here which has been talked about. Now, quality control test is what we are talking about when we say gallium 68, whether it is radiopharmaceutical, whether we can inject this into the patient or not. What we have to actually perform, the most important out of this is the radiochemical purity test to find out how much is the percentage of the free labeled free radio activity is gallium, whether it is labeled or not. Okay, so we have to know about this kind of concentration or the fraction of the impurity by using ITLC, instantaneous thin layer chromatography, and Watman paper also can be used, or silica gel ITLC, and this is the static phase. Again, this is a chromatography method as quite equivalent, or you can say with the same, almost same principle of static and mobile phase and getting the mobile phase out. But in the generator, it is about the production of the ink light. While here, it is about the finding out the different fractions, how much is the pure fraction and how much is the impure fraction. For that, we use this static phase of Watman paper or silica gel ITLC, and the mobile phase can be acetonitride, water, 1:1 proportion. There can also be a citrate buffer, and these things have been developed lately, and many developments have occurred to find out this QC test and to get it very fast and accurate results. And so citrate buffer is also another mobile phase which has been used, and on the basis of the retardation factor, we can find out how much is the gallium pure radiopharmaceutical, and generally the gallium radiopharmaceutical will be running with the solvent with the mobile phase, and it has a 1 as a retardation factor, and the unlabeled will be staying at the point of spotting or origin. So the free gallium, as I have told you, its retardation factor can be taken as 0. Generally, this is how it is, and so the lower zone will be the free radiopharmaceutical, which we don't want, and at the undesirable part fraction, and the label one will be the upper zone, and that is what is expected. If it has to pass, then it has to have at least more than 90% or 95% of the upper zone counts. When we count these two halves, we have to get the upper zone counts more. This is what is the expected. Then it will pass, and then we can inject this radiopharmaceutical into the patient's body. So, if radiochemical purity is less than 90%, then what can you do? You can purify it. That also has been designed. We can filter this preparation through the cartridge, which will hold the radiopharmaceuticals. See, the cartridge is like this. And then what can be done is, once this is holding, this is the pure fraction. Now it has been purified, and this can be eluted with 70% ethanol. Okay, and still this ethanol cannot be injected inside the patient's body, so you have to dilute it with the saline and passing it through the millipore filter so that it becomes sterile, and then you can use it for the patient's as a patient's injection. So this is how you can still use, although the yield becomes lesser now at every fraction, you are going to lose some activity and you will be losing time, but you can still spare, or you can still get a pure fraction which can be used for the patient. So, which are the trending gallium-68 radiopharmaceuticals? Out of such long list, like you can see ubiquitinin, RGD, transferrin, BTP albumin, albumin microspheres, macroaggregated albumin, FeOH thrice, colloid, alizarin, so on, so many. And the list is very long. But then the very important ones which are being used, or which are, you can say, the heroes of gallium-68 radiopharmaceuticals are gallium-68 DOTA and gallium-68 PSMA. The first one, DOTA, being the neuroendocrine agent, DOTA TOC, DOTA TATE, DOTA NOC. So many forms of this DOTA only are for neuroendocrine tracers, tumor tracers, and the PSMA is for the prostate-specific membrane antigens. So these two are the trending radiopharmaceuticals, as I can say. And for this, what are the parameters generally which have been designed? Of course, these are being developed being the latest radiopharmaceuticals which are in the trend. They have been optimized more and more over the period of time. As of now, these are the parameters which have been standardized, like the volume of gallium, the yield that has been obtained can be as much as 4 ml for both of them. The lichen PSMA, gallium 68 PSMA being much a stronger bond as compared to the gallium 68 total. Tate, talk or not. And that is a little more sensitive, as you can see, as I can explain as this point. And the ligand concentration for gallium 68 PSMA can be as less as 10 micrograms, while you need a little more, 25 micrograms for gallium 68 DOTAs. The reaction pH for both will be 4 to 4.5, and temperature boiling water bath for PSMA if the heating is not required, but it can enhance labeling if it is used heating. And this boiling water bath, it is very important here, the practical point to understand that for the gallium DOTAs when it is needed, both of them still, whenever you boil, the whole volume should be uh, totally drowned inside the water bath. The reaction vial should have the boiling water surrounded completely, and no level of the reaction mixture should have just air around it. So the whole thing should be immersed, the whole vial should be immersed properly inside the boiling water bath, and the time starts from the boiling of the water. So it is always important to know that this boiling water should be boiling of water should start as you are eluting the gallium 68 from the germanium 68 generator, because that will also waste time. So the boiling should be there in parallel, it should run. This is important because you have a 10 minutes to stand. Even if its heating is, where the heating is required, please start the boiling of water as you start the elution procedure. This is what it is. Okay, and this is for the manual labeling we are talking about. There are already automated labels where labeling possibilities, but the parameter setting also, preheating, whatever is required. It is important to know that the time has to be saved at every. Now, challenges of labeling. What really makes gallium radiopharmacy challenging? Because it is a lot of pure radioactive yield without any metallic impurities. It has to be freshly prepared, and the parent should not get into the yield, and that becomes a really serious problem. You cannot inject so much high radionuclidic impure heal inside the patient, because this is a long-lived parent. Okay, so we have to think about this. We should not. We should consider this as a point to be really looked into, and the quality has to be assessed before you really settle down with a standardized method. And so you have to keep checking the yield. What is the parental impurity at that initial stages? You have, and then the environmental conditions like the pH, temperature, and the reaction time also we have to standardize. And the conditions, pH especially, they can cause some kind of insolubility, and then the reactivity is lost of gallium. So the pH 4 to 4.5, and to settle it you need a buffer, which and then standardize the amount of buffer that has to be. All this becomes a requirement, or you can say not that it is impossible, but it is something which you have to get it hard earned to optimize this environmental condition. So the complex ligand chemistry for complexation of tissue of specific molecules, tissue specific molecules. So what this means is we should study very well which are the functional functions with which functional groups with which this gallium is going to bond, and its importance of it not getting broken inside the patient's body. So in vivo, and all these have to be studied very carefully. And as I've talked about the environmental condition, the pH optimization and amount of buffer required becomes important. This point I talked about the environmental conditions standardization. And then, so the temperature uniformity for the reaction also has to be set. As I told you, how will we get the uniformity? Only if the volume of the reaction vial or the whole volume is immersed inside the boiling water bath. Then you can get this kind of temperature uniformity. For the manual labeling, you have to consider all these points. So now to summarize this presentation, let me tell you what all we have seen. We have seen why we need to study this chemistry and what is gallium chemistry, what are the optimum conditions for labeling, the temperature, pH, reaction time, and the buffer addition, etc. And then the quality or control of radiopharmaceuticals, gallium radiopharmaceuticals, the radiochemical purity, the ITLC test, the chromatographic method, the list of gallium radiopharmaceuticals you've seen, and what are the challenges of labeling with gallium. The reference I've used for this presentation is PET chemistry, the driving force in molecular imaging, the editors being P.A. Schubiger, Lemon, and Free. So if you have any queries or anything that you want to share with us, please mail to us at support@nuclearmedicinesolutions.in. Thank you.